All right, welcome back Physics C students for our third notebook video on work, energy, and power. We're going to go over some potential energy derivations here, including spring energy and two different ways to get gravitational energy. We'll be using one or both of these, each of the derivations. The first formula here, delta U, is the negative integral from A to B of a conservative force, which has to be as a function of position, dot product with the little path element dr. And we can simplify the dot product here by taking f dr cosine theta. Theta here would be the angle between the force and our displacement, our little tiny displacement element, and f and dr here are magnitudes. The other formula we'll use is a conservation of energy statement, mechanical energy. Delta K plus delta U equals work external or non-conservative. So for spring energy, here's what we're going to start with. We start with a spring attached to a wall, and we're going to go ahead and define this location here as being x equals 0. This is going to be state A, and our spring is going to be unstretched. And then later on, our spring is going to get stretched out and here was 0, and we're going to be at some new location. Let's just call that x. So we're going to start with the top formula, where we have U of the spring is going to be negative integral from A to B. We'll simplify the dot product. We have the force of the spring times dr times cosine theta. And the force of the spring is in magnitude kx, where x is the amount that it stretches from equilibrium. I'm going to multiply that by dx, and then we have cosine of 180. And why is that cosine of 180? Well, it's cosine of 180 because the spring here is pulling to the left, but our motion was to the right. And this is state B. So in going from A to B, we have moved to the right, but the spring was pulling back to the left, and that's an angle of 180. So this becomes -1, and that negative will cancel with the negative that we had out in front. So now we get the integral from A to B of kx dx. And remember, the two negatives canceled. K is the spring constant, so that comes out. We're left with the integral from A to B of x dx, which is x squared over 2. We evaluate this from A, B. Remember, B was at x, A was at 0, and we end up with our old familiar formula, 1/2 k x squared. So there we have quick derivation of the potential energy associated with a spring. This would also be true for an elastic band or bungee cord, which is modeled using the same type of force. Next, we're going to move on to a gravitational energy derivation. For this derivation, we're going to let g be constant, which means we're near the surface of the Earth or a planet or a moon. Basically, we have a small change in height. I put small in quotation marks because small is a relative term. Small compared to what? This is small enough that it does not change the value of g. That's the primary thing here, that g is constant. So, what is this going to look like for us? Well, we're going to start with a mass at position A, and this time I'm going to have a hand move this up to position B. So someone's going to lift this mass up. And we're going to look at this in two different ways. The first way that I'll look at this is by using delta K plus delta U equals work external or non-conservative. Now, an important thing to note about this example is that we're going to do this when we move from A to B. We do this at constant speed. So our acceleration is 0, and because of that, we know that the force of the hand in magnitude is equal to the force of gravity in magnitude. So the hand has to push up, same as gravity pulls down, so that we have no acceleration. Because of that, we have no change in kinetic energy. We don't change speed, so no change in kinetic energy. We're going to get delta U, going to be gravitational energy, and the work from an external or non-conservative force here is the integral from A to B of the force of the hand, because that's the non-conservative force. It's an applied force, non-conservative, times, I'm going to use dy because we're moving vertically. And cosine this time is going to be cosine of 0 because we are moving up and the hand is pushing up. The angle between up and up is 0. So that becomes 1. We're left with the integral from A to B. Remember, the force of the hand in magnitude was mg dy. The mg is constant, so that comes out. Integral from A to B of dy delta U gravity. Oops. My U is not working out here. Okay. Delta U gravity equals mg y evaluated from y equals A, y equals B, and we get mg yb minus ya, which is mg delta y. And that's the equation that's on the equation sheet. Right? That was delta u g. Just go back up here. This was the potential energy of the spring. Now, I'll show you another way of doing this derivation, and that is to use the other definition that delta U is the negative integral from A to B of the force, which is the conservative force, dy cosine of theta. In this case, we have the force conservative, which is gravity mg, dy, but now theta is the angle between the conservative force and the direction we're moving. Now gravity pulls down, but we are moving up, and that is a direction of 180. So that will become -1, which will again cancel with the negative in front. So we're left with the integral from A to B of mg dy, and that should look familiar because it's going to dump us right back here, and we will get the same answer, right? Takes us to the same place. So there's two different ways of deriving this simpler version of gravitational energy. And our last little derivation is going to cover more of a universal gravitation, where we're dealing with very large distances where g is not constant. The distances that you move over are so large that the value of g changes in some kind of significant way. So the basic setup for this is that we've got a rocket ship here. Maybe this is a NASA rocket or something. It's in position A right now. It's at a distance of r from the center of M1. Maybe that's the Earth or whatever. And this rocket here is going to go on out to infinity, which is going to be location B. And at infinity, we're going to define the gravitational at infinity defined to be 0. We talked about this a little bit earlier, but the reason why we define gravitational potential energy in a universal sense to be 0 at infinity is because this works for all astronomical objects, no matter how big or small. It works for planets as they change their orbits. It works for, as you could say, galaxies that are colliding. It could work for a rocket ship. Anything really, hitting a golf ball off the moon, any objects, no matter how big or how small, 0 at infinity works for all of them. Just like the little derivation that we did, we're going to do this at constant speed. And if we're at constant speed, then we know that our acceleration is 0, and we know that the force of the rocket here is equal in magnitude to the force of gravity. Now for this derivation, I'm only going to do this one way, and that's starting with delta K plus delta U equals work external non-conservative. Because we're not changing speed, our delta K is going to be 0. This is going to give us delta U gravity, and that's going to equal the integral from A, which was at a distance of r, to B, which is out at infinity. The force of the rocket ship has to be G M1 M2 over r squared. That's the force of gravity, and the force of gravity was equal to the force of the rocket ship. The force of the rocket is the non-conservative force, which is doing work here, dr. When we go to evaluate this, g, m1, and m2 are constants. That leaves us with the integral from r out to infinity of dr over r squared. You could think of that as r to the negative second as well. The delta u here becomes u g b minus u g a, right? The potential energy at B minus the potential energy at A, final minus initial, always for delta. That's going to equal G M1 M2, and the integral of 1 over r squared dr becomes negative 1 over r, and this is going to be evaluated from r to infinity. When I evaluate this, I get negative g m1 m2 over infinity minus negative g m1 m2 over r. This term is 0. These two negatives cancel each other out, and we're left, and remember UGB was defined to be 0 as well. We said no potential energy at infinity. So what we get is UGA, negative UGA, equals positive G M1 M2 over R, which, if we move that negative sign around, we get the gravitational energy is negative G M1 M2 over R. And we should ask ourselves, does this make sense that our initial energy was negative? And it should, because just like here, when we raise the ball up, we are doing work against gravity, right? The hand here is doing positive work, so it is increasing the energy as we increase the separation. Well, that's the same thing here. Instead of a hand, we have a rocket, but that rocket is pushing in the direction of motion, so it's doing positive work, so it should increase the energy. Now, if we end with 0 energy, we must have started with negative energy, because when you increase a negative, you can get to 0. And I think that is the clearest, most simple to follow derivation for this sort of gravitational energy. There are other ways of doing this, including this method where we integrate the conservative force. But those other methods get a little messy with some of the vectors and the definitions for certain types of vectors. So I'm going to avoid those, and I think this is something that's easy enough for everyone in Physics C to follow along with. That's it for this video, just these 3 derivations on this page. I look forward to seeing you soon. Have a great night, morning, evening, weekend, weekday, summer, winter break, whatever it is. I hope you're doing well.